Assalamualaikum, my name is Muhammad Fikri Rahman bin Isa. My matrix number is CN240135. We are from Group 4 and our project title is Earthquake Monitoring System using Microcontroller. We move to problem statement. Earthquakes can happen at any time and even little ones can cause a lot of damage to buildings, power outage, fires and injuries. Most of the earthquake detection systems available in Malaysia right now are controlled by the government, are expensive to set up, and are not meant for users in home or communities. Because of this, a lot of people are still unaware and unprepared when earthquakes happens, which makes them panic, slow down evacuation and cause more damage. So, there is a very important need for a low cost, easy to use and real-time yearly warning system that can find dangerous ground vibrations and let user know right away using IoT connectivity. By giving people a few more seconds before heavier shaking happens, this kind of device can help people get ready for disaster, preserve property and save lives. For our objective, the first one is to implement a seismic detection logic using the MPU6050 sensor and ESP32 by monitor ground vibration and trigger alerts when safety thresholds are exceeded. The second one is to develop a prototype for earthquake detection that combines the ESP32 microcontroller with vibration sensors. The third one is to develop an alert system using Telegram that sends instant notification to users' smartphone when an earthquake or unusual ground vibration is detected. For our scope, the first one is the project is limited to using an ESP32 to detect vibration in real time based on a set threshold without using AI or advanced hardware and is made only as a simple educational prototype. Second one is the prototype will be limited to combining ESP32 with a simple vibration sensor which is MPU6050 and it will not include large-scale production or commercial-grade hardware development. The third one is the alert features will be confined to send notification to Telegram only and will not extend to other communication platform or emergency response teams.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Engku Luqman Omar bin Engku Ahmad Faisal. My matrix number is CN240042. For the literature review, we studied previous earthquake detection systems to understand how they were designed and how they perform. This helped us recognize the advantages of the existing system, such as fast detection and early warning features, as well as their limitations, including high cost, limited accuracy, or delay alerts. Based on this finding, the literature review guided our project design by helping us choose suitable sensors, a microcontroller, and an effect alert mechanism that fit our project requirements. It ensured that our system design was practical and based on proven approaches. In addition, reviewing past research helped us prevent redundancy by avoiding methods and design that have already been implemented. Instead, we focus on improving and adapting existing ideas to develop a more efficient earthquake detection system.
So about this project presents an automated earthquake detection system using an ESP32 microcontroller and vibration sensor. The system continuously monitors ground motion through MEMS accelerometer and identifies abnormal vibration based on predefined threshold. When seismic activity is detected, alert mechanisms such as buzzer, LED display and wireless notification are activated in real time. The system is designed to be low cost, energy efficient and suitable for long-term monitoring. By providing fast and reliable early warning, the proposed solution enhance safety, improve preparedness, and demonstrate the effectiveness of microcontroller-based technology for disaster mitigation.
Hi, Assalamualaikum. My name is Siti Nurfatiha binti Ruli. My matrix number is CN240193. So, today I will explain about the block diagram. This slide shows the basic block diagram of the earthquake detection system. Although the diagram is simple, the system operation involves several detailed processes. The system begins with the MPU 6050 sensor, which continuously detects vibration or ground movement and measures the strength of the vibration. The vibration data is then sent to the ESP32 microcontroller, which acts as the main processing and control unit. The ESP32 analyzes the incoming sensor data and compares it with the predefined threshold values to determine whether the condition is normal or indicates a possible earthquake. Based on this decision, the ESP32 controls the output devices. When no vibration is detected, the green LED is turned on to indicate normal operation. When vibration is detected, the red LED and buzzer are activated as an early warning. At the same time, the vibration magnitude is displayed on the LCD, so users can clearly observe the intensity of the vibration. For more serious vibration levels, the ESP32 activates a relay that functions as a switch to turn on the mini siren. The siren sounds for a fixed duration to alert nearby users. In addition, the ESP32 sends a notification through Telegram via Wi-Fi to inform users remotely about the detected vibration. A reset button is also included, allowing the user to manually stop the siren and return the system to its normal state without waiting for the preset alert time. So I think that's all for the block diagram. Thank you.
Next, we go to the flowchart. This slide shows the flowchart of our earthquake detection system using a microcontroller. The system starts by initializing all the necessary variables, such as the pins for sensors, LEDs, buzzer, and buttons. Once the system is powered on, the LCD displays a message indicating that the project is active and ready to measure earthquake magnitude. Next, the system continuously checks the sensor for any earthquake activity. If no earthquake is detected, the green LED stays on and the LCD displays no earthquake detected. However, if an earthquake is detected, the system calculates the vibration magnitude using data from the sensor. Once the magnitude is calculated, the red LED turns on, the green LED turns off. The buzzer is activated and the LCD displays the earthquake magnitude. After a short delay, the system triggers the siren and sends a notification via Telegram to alert users about the detected earthquake. Finally, the system returns to monitoring for the next possible earthquake event, making it ready for continuous detection.
So next, I will explain about the layout design. The overall prototype is designed as a compact earthquake detection system with a miniature house structure to provide a clear visual representation of the components and their functions. The 3D view illustrates the complete internal arrangement, including key elements such as the vibration sensor, ESP32 microcontroller, LCD display, relay, LEDs, buzzer, mini siren, push button and smartphone integration for Telegram-based alerts. Based on the front and side views, the model dimensions are 10 cm in height, 25 cm in both width and length, demonstrating a well-organized and space-efficient design. The components are systematically positioned on a stable base to ensure proper wiring, accessibility, and smooth operation during testing. Meanwhile, the top view provides a clear overview of the spatial arrangement, avoid interference, and improve functionality. Overall, the combination of all four views presents a functional and educational prototype that effectively demonstrates the working concept of an earthquake detection and warning system, making it suitable for demonstration and academic reporting. So that's all from me. Thank you.
So we move on to list of hardware we're using in this project. So the first one, we're using ESP32, around 25 ringgit. So it acts as the brain of this project. It controls all other parts and connects to Wi-Fi to send message. And then LCD, 5 ringgit 50 cent. It acts as the screen. It shows the vibration level. And then DC motor, 3 ringgit 90 cents. It acts as the simulator to fetch an earthquake for testing, and the potentiometer, 3 ringgit 50 cent. It acts as manual control knob for DC motor. By rotating the potentiometer, the user change the resistance in the circuit, which regulate the speed of the motor. And then buzzer, 3 ringgit. The buzzer beep for small shake. And then the sirens scream for a big one. Then we move on to relay, 5 ringgit 30 cent. It acts as a switch. It turns on the loud siren because the siren need more power than the ESP32 can give directly. Then push button, 1 ringgit 10 cent. The manual trigger. And then the MPU 60550, around 20 ringgit 50 cent. So it acts as the sense organ. It detects ground vibration and measure how strong the earthquake is. And then motor driver, 6 ringgit. So it helps the ESP32 control powerful motor safely. And then battery, provide the necessary power supply. And then the last one, LED, around 60 cent. So the green LED indicate normal condition. For the red one, it lights up when vibration exceed the set threshold. So we move on to the list of software we're using for this project. So the first one is Arduino. Arduino Integrated Development Environment, IDE, is an open source software used to write, compile and upload programs to Arduino compatible microcontroller. It enables developers to control hardware components and include tools such as the serial monitor for debugging and real-time data observation. Second one is Telegram. Telegram is a cloud-based messaging platform recognized for its speed and security. And third one is Proteus. Proteus is comprehensive electronic design automation (EDA) software used for schematic capture, simulation, and printed circuit board layout design. Its key feature is the ability to simulate the behavior of microcontroller and electronic components digitally before they are physically assembled. And then for one, the Tinkercad is a free web-based application developed by Autodesk, widely used for 3D modeling and introductory electronic simulation. And then the last one is Walkwi. Walkwi is a browser-based electronic simulator for IoT and embedded system development. It allows real-time simulation of popular microcontroller and support network features.
Assalamualaikum warahmatullahi wabarakatuh. I want to tell about our hardware result. This project is an earthquake detector system designed in the shape of a house, using an MPU 6015 sensor and ESP32 microcontroller to detect ground vibration and movement. When an earthquake is detected, a siren is activated to provide an early warning alert.
Okay.
Now we go to data table and graph. This slide shows the relationship between the test number and the total vibration magnitude measured during our experiments. On the left, we have the data table showing the vibration readings along the X, Y, and Z axes for each test, as well as the calculated total magnitude. On the right, the line graph visually represents the total magnitude for each test. From the graph, we can see that the total vibration magnitude fluctuates across different tests, with the highest value observed in test 1 and 10. This indicates variability in the random vibration detected, which help us understand how the system responds to different vibration conditions. Overall, the data confirms that our sensor and microcontroller setup can effectively measure vibration magnitudes and reflect changes in the environment accurately. Next is the table for functionality tests. This slide shows the result of the system functionality testing. The table on the left compares the expected and actual outputs for each component. The visual alert, audio alert, IoT alert, and display were all tested by applying vibration above the threshold. In each case, the system responded correctly, the LEDs operated as expected, the buzzer and siren activated, the telegram alert was received, and the LCD displayed monitoring. The pie chart on the right summarizes the result, showing a 100% pass rate for all 5 tests.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Today I want to tell about discussion for our group project. We use the MPU 6050 sensor was used by the earthquake detector system to successfully detect vibration, and the ESP32 microcontroller process the data. The LEDs, buzzer, siren, LCD display and telegram alert were all correctly triggered by the system in response to the simulated vibration. This demonstrates the system's ability to distinguish between typical and anomalous vibration in real time. By enabling remote monitoring, the IoT feature increases use owners. However, the accuracy of the system is dependent. The threshold system strength may be impacted by non-seismic vibration, so it is best suited for educational small-scale application.
So next I will explain about the achievement of the objective. All objectives set at the beginning of this project were successfully accomplished. The first objective was to implement seismic detection logic using the MPU 6050 sensor and ESP32 to monitor ground vibration and trigger alerts when safety thresholds were exceeded. This was achieved by continuously reading vibration data and processing it in real time. When abnormal vibration was detected, the system responded immediately by activating the alert mechanisms. The second objective was to develop a functional earthquake detection prototype by integrating the ESP32 microcontroller with a vibration sensor and other output components. This objective was achieved through successful hardware and software integration, resulting in a stable and fully working prototype. The third objective was to develop an alert system using Telegram that sends instant notification to the user's smartphone. During testing, the system successfully sent real-time alerts with vibration magnitude values where the earthquake-like vibration were detected. Overall, this result confirmed that the objectives were achieved and the system functioned as intended. So, I think that's all from me. Thank you.
Okay, I want to tell about our conclusion. Using ESP32 and MPU 6050, this project successfully created a low-cost Internet of Things earthquake detection system. Real-time vibration detection and prompt alert via visual, audio, and telegram notification are offered by the system. The prototype shows great promise for early warning application and can be further refined for broader real-world use, despite its limited precision when compared to professional equipment.